Okay, good morning. So we're going to make a video here, and you're going to just watch this in class, and we'll maybe answer some questions about it when you're done watching it. But this is a big day. This is going to be the day where we learn the fundamental theorem of calculus, both parts. One of the end goals of today is really, if I give you a function or a problem like this, x squared plus 2x, and I say, what's the integral of that from 0 to 4? But after today's video, you're going to know how to compute this by hand. Now, right now, you can compute that on Desmos perfectly fine. Ain't no thing. Type it in, get an answer, but you're going to learn how to do it by hand. Okay? But we're not going to just jump right into that. We're going to build up to it. Like I said, there's two parts to the fundamental theorem. Calculating that by hand is one of them. And then the other part we're going to talk about right now. So, and we've already kind of been talking about the other part. You just maybe not realize it. So we're going to go back and tie some of these ideas to all the various problems that we've done in the past. So we'll start with the oil in the lake. Okay? So the oil in the lake. If you remember the oil in the lake problem, you had oil that was leaking into the lake at a rate of 2,000, and it was being sucked out of the lake at according to some function. Okay? Now, I don't know that we ever wrote this expression down for the oil in the lake problem, but let's talk about what does this mean right here. Okay? This is the rate in and the rate out. Hopefully by now you understand that when you integrate a rate of change, you get the change in some quantity, right? That's what happens, okay? But now if you notice, I've created this function that the variable, the independent variable, is up here in the exponent, okay? This function right here, very similar to the snow function, but this function, okay, this is the function that will tell, or I say give, that will give the amount of oil in the lake for any time, okay? And this function is assuming the lake was empty when O, D, and R showed up, when the pump was turned on. Okay? If it wasn't empty, we would have a number out here, like however much oil was in the lake when we started the pump. Okay? But this is a function that will give the amount of oil in the lake for any time. Okay? Now, my question for you guys is, this is a funky looking function, okay? And we learned last time that this is actually an antiderivative, okay? If I asked you, what's the derivative of this function? You would say, well, if this is the function that tells the amount of oil in the lake, the derivative is going to be the rate of change of oil in the lake. Well, we know the rate of change of oil in the lake. It's 2,000 minus 400 radical t, the rate in minus the rate out. Okay? So the derivative of this function right here is 2,000 minus 400 radical t. So this function right here must be an antiderivative. It's a weird way of writing it, but this function right here must be an antiderivative of this function right here. So m of t is the antiderivative of 2,000 minus 400 radical t. Okay? All right, let's look at the next problem. The stink bugs. I was surprised I got no comments about the stink bugs on anything. Like, I hate those things. Okay, so I'm going to write this function here. B of t equals 450 plus the integral from 0 to t of 5 radical x cosine of x over 5 dx. Okay? So what is that function right there? What is this function right here that we're looking at? Okay? Hopefully you recognize that as this is the function that will give the amount of bugs in the house for any t. Okay? This is the function that will give the amount of bugs in the house for any t. We started with 450, and then this quantity right there is how much bugs you added or subtracted from 450. So you put those two together, and that'll tell you how many bugs there are at time t. Okay? But now, what I'm interested in is what's the derivative of this function right here, this b of t. What's the derivative of it? Okay? Well, if that function represents the amount of bugs in the house for any time t, the derivative of that function would represent the rate of change of the number of bugs in the house at any time t. And you know that. The derivative of that function is 5 radical t cosine of t over 5. Okay? Now, don't get hung up with the fact that this is not an x. This should be a t. Remember, if b is a function of t, then b prime should be a function of t. Okay? Remember, when I have this inside the integral like that, I just have to make this a different variable, something other than t. Okay? And that's why I chose x. That's sort of the convention. Oftentimes, what you'll see in these types of integrally defined functions, you'll see one of these as an x and then the other one as a t. Okay? I chose to use the independent variable as t because all of these things tended to be in terms of time. Okay? So we have this function here, b of t, and the derivative of it is that. Okay? And I want you to notice, like, the derivative of this function m, what was it? The derivative of this function b, what was it? See if you're seeing a pattern here as we go through this. Let's go to the Kings Island problem. Okay, I'm going to pause, just save you guys. Okay, so I've got a clean board here. Let's talk about the Kings Island problem. I'm going to write a function here. We never wrote this function with the Kings Island function, but I'm going to write it. I'm going to put the 0 in. I didn't do that on the oil problem. 0 plus the integral of 0 to t of e of x minus L of x, okay? I don't remember what E of x and L of x were, and honestly, I was just too lazy to look them up. But E was the rate that the people were entering the park, and L was the rate that people were leaving the park, okay? So what does this function right here? Well, what does this function right here represent? Well, this is how many people were in the park at t equals 0, which was 9 a.m., and then this was how many people were added to or taken out of the park between 0 and t. So this function represents is the number of people in the park at time t, or for any time t, okay? And of course, I'm going to ask you the same question I've asked you on the last two. What's the derivative of this function? What's the derivative of this function right here? Well, if that function represents the number of people in the park at any time t, the derivative would represent the rate of change of people in the park at any time t. And we know that. We were given that. The rate of change is the rate that they're entering minus the rate that they're leaving. Okay? So this function p is actually an antiderivative of e of t minus L of t. It's just a weird way of representing the antiderivative. It's a special antiderivative. It's a special antiderivative that identifies the chips. The chips are right here. It's saying, I know that at t equals 0, there were 0 people in the park. Okay? That's like that initial condition, that initial value, okay? And then lastly, the next one that we talked about, the shovel problem or the snow problem, okay? We already talked about this, but just to tie it together, here's this function, 250 plus the integral from 0 to t of 5 minus 50 over 0.01 x plus 1 dx. And what does this represent? Okay, this function is the amount of snow in cubic feet on the driveway for any time t. The amount of snow on the driveway for any time t. Okay, and then I'm going to ask you the same question I've asked on the past three. This is a function, right? This is a goofy function. It looks funny. It's the variable's up in the integral sign. We call that in the bound of the integral. Okay? What's the derivative of this function? Well, you know what the derivative means. It's the rate of change of the amount of snow in the driveway in feet cubed per minute. And you know what that is because you were given that information. It's the rate that the snow was falling minus the rate that we was shoveling. Okay, so 5 minus 0.01 t plus 1. That was the rate in, and that was the rate out. Okay? So these functions that look like this, where you've got a variable in one of the bounds of the integral, okay? We have different names for these. These are special kinds of ways of representing antiderivatives. Sometimes we call these area accumulator functions. But this leads us to the first part of the fundamental theorem. And when I'm done talking, I'll erase. But what the first part of the fundamental theorem is going to tell us is when we have a function like this that's defined this way, how we find the derivative of that function. Okay, so let me pause and erase, and then we'll... Okay, so what we're going to do now is we're going to generalize what we just kind of experienced in those past four scenarios. So in general, if f of x equals the integral from a to x of f of t dt. Now, notice I changed this. I changed this just to show you that you can. Okay? Now this is a function of x, not of t. And then you're integrating some function here, and this function that you're integrating, little f, this variable here, f of t, it could be any variable you want. It's actually called a dummy variable. You can make it anything you want. Okay? But if you've got a function that's defined this way, then the derivative of that function. Okay, so think back to what we just did. What's the derivative of this function right here? It's just going to be little f of x. Okay? Literally what happens here is to take the derivative of a function like this, you just take what's up here and stick it in for x. Now, I don't want you just to think, oh, this is what I do to get an answer without understanding kind of what's going on. But that is what happens, okay? If you have a function like this, the derivative is just little f. Because realistically, what big F is here is actually an antiderivative of little f, okay? That's what big F is. It's just an antiderivative of little f. So the derivative of an antiderivative is the function you were starting with, okay? So this is what we call the fundamental theorem of calculus, which our book identifies as part 1. Okay? Some textbooks identify this as part 2. It just all depends on how they introduce them. Okay? okay? So this is the first part of the fundamental theorem of calculus stated in words. Now we're going to look at maybe this idea, but we're going to look at it graphically, okay? So let me pause and set up. Okay, so we're going to look at this idea graphically. So what I've done here is I've drawn a graph, and this is of some function f, okay? So I'm going to give you a second. I'm going to go fill up my coffee and give you a second to draw that graph. While you're at it, take note that the horizontal axis is not labeled. Okay? I didn't say that this is f of x, f of z, f of p, f of q. It's just the function f. But you all certainly could tell me, you know, by looking at this graph, if I put some y values on here, you could tell me what's f of 4. Well, f of 4 is whatever that is. F of 2 is 0. Okay? It doesn't matter if it's f of x, f of t, f of p, or f of q, or whatever. All right? So now, I'm going to define this new function, and I'm going to call him big F. And I'm going to say that big F is going to be the integral from 0 to x of f of t dt. Okay? The integral from 0 to f of t dt. And so what we're doing is big F is accumulating area. So as we start here at x equals, or at 0, we're going to add area up from 0 to whatever x value you want. So like big F of 1, just to make sure you understand, would be the integral from 0 to 1. So big F of 1 would be, it'd be the area that's accumulated from here to here. Okay, and I don't know what that is. We'd have to do pi r squared or whatever. Okay? Big F of 2 would be this area right here. Or this integral, which is going to be all that area. Okay? But what the fundamental theorem of calculus says is that big F prime of x is equal to what? F of x. So realistically, what's happening here, when I define this function here, his derivative is actually this graph. This graph right here is the derivative of this function big F. Okay? So if you think back to some of the questions that we had back in the day when I would give you a derivative graph and then I would ask you about the function, this is what's going on here. Like if I could ask you questions about big F now, I could say, well, tell me where big F is increasing. Oh, well, it's increasing where his derivative is positive. So between 1 and 2 and 3 and 4. Where's big F decreasing? Oh, big F is decreasing when his derivative is negative. Oh, between 2 and 3. Where's big F have a local max at x equals 2 because his derivative changes from positive to negative. Okay? So this graph right here is the derivative of this function big F. Okay? So that's another way of looking at it. And then like what would big F double prime be? It would be little f prime. So if I asked you about big F's second derivative, you would have to know about little f's first derivative. Okay? So that's just another way of looking at this Fundamental Theorem of Calculus Part 2 graphically. But we still have this statement here, okay? That big F's derivative is just that x goes down there and it's little f, okay? All right, let me pause this and we'll do some examples. Okay, so now we're going to look at some examples of this first Fundamental Theorem of Calculus, Part 1, I should say. We'll look at some examples algebraically. So here we go. Example number 1, we'll say, let's let big F of x equal the integral from 2 to x of sine squared t dt. what's big F prime? Okay. Now, honestly, these problems will be the easiest for you to compute, and they may be some of the hardest to conceptually understand. But to get the answer to this, like, literally, it's just this. And the x just comes down in for the t, and it's sine squared of x. Okay? Because this function right here, this big F function, is really a funny way of representing an antiderivative of sine squared of x. Okay? How about another one? How about this? Let's say that big F of x is equal to the integral from 3 to x of 1 over t plus 1 over t cubed dt. What's the derivative of this? Literally, it's just 1 over x plus 1 over x cubed. Okay? Literally, it's that simple. Let's make one that's a little bit more challenging. Let's say that big F is equal to the integral from 0 up to x cubed. Now we're going to do a composition. E to the t plus cosine of t. Okay? So now we've got a composition. This isn't just like, you know, an x up there, it's an x cubed. Okay, so the chain rule is going to come into play. How do we execute the chain rule for derivatives on this? Pretty simple. Okay, you just still bring this down, e to the x cubed plus cosine of x cubed, like that. And then what are we going to do? We're going to multiply by, guess what? The derivative of x cubed. And there you go. Okay, so if you've got a function of x up here, you're just going to stick that in there and then multiply by its derivative. Okay? Again, these are really, really easy to get the answers for. To find these derivatives of these types of functions, very, very easy. Where this gets a little bit more complex is when you have to start making connections between the different functions, like that graphical problem. That's a little bit more complex, but all dealing with the same concept of the fundamental theorem of calculus. Okay? So I'm going to pause this and erase, and then we'll talk about the second part of the fundamental theorem of calculus. Okay, so here we're going to talk now about the second form of the fundamental theorem of calculus, and it's going to start with like something like this. We need to learn how to compute a straight-up integral, like this. Say if I said 1 to 4 of, I don't know, x squared dx, okay? We need to learn how to compute that integral outside of sticking it into Desmos or our calculator, okay? Now, there's one, a graphical interpretation of this integral could be that area right there. Okay, that is one graphical interpretation of this integral, but I don't want us all to live in the world that integration is just areas. What we really need to make sure that we're understanding is that integration is adding stuff up. In this case, what we're doing is we're adding up rectangles that are f of x high and infinitely thin, and we're going to add up an infinite number of them between 1 and 4. Okay, and that happens to be this area. Okay, when we get into second semester, we're going to look at integration in a whole different way, where we're going to be adding things up that aren't rectangles, but will still be integrating. Okay, and we need to know how to compute these guys. Okay, so the question is how am I going to compute this? Okay, how am I going to compute this? Well, we would know how to compute this if this function x squared represented a rate of change. If x squared represented some rate of change, then we would know that the answer to this would be the change in whatever function f of x's rate of change was. Okay? So what I'm going to do is I'm going to think about some function, big F, whose derivative is x squared. Okay? And if I think about that function, and I think about this and say, okay, well, now I'm integrating a rate of change. I'll think about this like a rate of change. And what do I get when I integrate a rate of change? I get the change in the quantity. So whatever the answer to this is going to be the change in big F. Okay? So the answer to this integral right here is going to be the change in the function whose derivative is x squared. Let me say that again. The answer to this integral is going to be the change in the function whose derivative is x squared. Okay? Now, can you think of a function whose derivative is equal to x squared? And the answer is yes, you can. It's the antiderivative of x squared. That's why we learned some of those antiderivative techniques right away, so we would be able to make these connections. Okay? So the antiderivative, this big F function that we're talking about, is x cubed over 3. Okay? So I just find x cubed over 3, and then oftentimes what we do is to denote that we're going to evaluate x cubed over 3 between 1 and 4. You put it in brackets like that, and then you put 1 and 4. That indicates to the reader that, hey, I'm going to evaluate this. It's the change. It's the difference between those two. So that's 4 cubed over 3 minus 1 cubed over 3, which 4 cubed is 4 times 4 is 16 times 4 is 64 thirds minus 1/3, which is 63 thirds, I think. Okay, so 63 thirds is the answer to this integral. Remember, a definite integral has a definite answer, 63 thirds. That area, if we want to think of it that way, is equal to 63 thirds. Okay? So, what is all this? Let's generalize all this into sort of the other part of the fundamental theorem. Let me pause so you don't have to watch me erase. Okay, so here we go. Welcome back. We're going to generalize this and say this is the fundamental theorem of calculus. The second part, okay? It's not the sequel. It's not. I wouldn't say it's like the sequel. The first part and the second part are really just two completely different ways of saying the same thing. And for me to prove that is, I can't do that through a video. Like, I think I need to be able to like talk to you and have some conversation. So these two parts are essentially equally valued. It's not like the sequel and the original. You know, they're both equally important. So here we go. We're going to say, let's let big F of x be any antiderivative of little f of x. Okay? The integral from a to b of little f of x dx. Okay? How we compute an integral, how we compute a definite integral to get a numerical answer is equal to big F of b minus big F of a. Okay? So we got to find the antiderivative and then plug in a and b and subtract them. Okay? And where that comes from goes back to the idea that we had been working with, that when we integrate a rate of change of some quantity, we get the change in the quantity. We get the difference in the quantity. Okay? So what we do is we just think of this function right here as a rate of change of some quantity. And then we work backwards to figure out the function whose rate of change this is. Okay? It's the antiderivative. Okay? So let's do some examples of this. Just computing these suckers. So we'll say the integral from 2 to 5 of x squared plus 2x. Okay? So we're going to compute this integral. In fact, the textbook that we're using actually calls this second part of the fundamental theorem the computation theorem, the computation rule. It tells us how we compute a definite integral. Okay, we're not going to just stick this in Desmos to compute it. We're going to actually compute this one by hand. Now, some of the harder ones we will compute on Desmos, because this technique, okay, this technique, I will say before we get into this example, but this fundamental theorem, being able to compute an integral this way, relies on you being able to find the antiderivative on your own. If you can't do that, then you can't do this. So we have to do problems here that we can find the antiderivatives of. Okay, that's one of the reasons why I've been giving you antiderivative quizzes over the past couple classes. Okay, so what we're going to do is we're going to find that antiderivative. All right, so I'm going to do each one of these term by term. I'm going to say, okay, well, the antiderivative of x squared is x cubed over 3. The antiderivative of 2x is x squared. And now I'm going to put brackets around this. That indicates to the reader, this is my antiderivative, and then I'm going to evaluate this between 2 and 5. Okay? I'm going to find the difference between those two. So that'll be 5 cubed over 3 plus 5 squared minus 2 cubed over 3 plus 2 squared. Okay? Now, I'll be honest with you. This is the part of the fundamental theorem of calculus that I hate and I suck at, because I really suck at arithmetic, and like this is a lot of arithmetic. So a lot of times what I would do when I learned this, and I won't judge you if you do, I would write this out on my paper when I learned this, and then I would write this out on my paper, and then I would use a little scientific calculator to do all this arithmetic. Okay? And just for time's sake, I'm not going to do all this arithmetic. I'm just going to tell you that this ends up being 60. Okay? So the value of this integral right here is equal to 60 if we actually did all that arithmetic. Okay? All right, let's do another one over here. I think I can fit it right here. So another example. The integral from 0 to 2 pi. Just heard a noise. Oh, sorry. The integral from 0 to 2 pi of sine x dx. Okay, let me pause this. Okay, sorry about that. Mr. Renshaw came in. So we're going to compute this guy right here. If we want to do some sort of graphical interpretation of what this might be, okay, that's the sine function. So we're finding, if we wanted to think about this as area, we would be thinking about this as the area from there to there. Okay? But this is one of the problems with just thinking about area, because what we're really doing here is we're summing up these y values times an infinitely thin change in x value. We're making these y values times that infinitely small rectangle. Well, the y values here are all positive, the y values here are all negative. So you might be able to suspect what the answer to this problem is going to be. You probably are suspecting, I hope you're suspecting, the answer is going to be 0, but let's prove it. Okay? So if we're going to do this using our fundamental theorem, we find the antiderivative of sine of x, and we know it's negative cosine of x. And then we're going to evaluate that from 0 to 2 pi. And then I'm going to just go right underneath here because I don't want to run out of room on you. So that's going to be negative cosine of 2 pi minus negative cosine of 0. Okay, and I think it's okay right now for us to write minus minus. That way we don't make a sign error, S-I-G-N error. Just go ahead and write minus minus and then clean it up later. Okay, so this is negative cosine of 2 pi, so the cosine of 2 pi is 1. Minus minus is plus, and then what's the cosine of 0? 1. Negative 1 plus 1 is 0. Okay? Which, now, if you actually go up here and see this, you could maybe conjecture that, is it possible maybe this area right here is 1 and that's negative 1? How might you prove that? Instead of integrating from 0 to 2 pi, why don't you integrate from 0 to pi and see what happens? Okay? All right, let's try another one, but I'm going to pause before I do another one to erase the board. All right, we're back. One more example here of just computing a definite integral. You can see that the hard part of this is going to be being able to compute these antiderivatives. So let's do 1 over t plus 1 over t squared. Okay, and I'm using a different letter there just because I can to help get you comfortable with, looking at these things with different letters. It doesn't always have to be an x. Okay, so here we go. First step is to find the antiderivative of this function here. So the antiderivative of 1 over t is the natural log of t, plus, and then the antiderivative of 1 over t squared, you've got to think about that as t to the negative 2, and then anti-differentiate that, add 1 to the exponent and flip it. That's going to be negative t to the negative 1, okay? And then I'm going to evaluate this from 1 to 10. I just thought of something that maybe you were thinking. When we do these antiderivatives on your quizzes and stuff, I always talked about the chips, plus c, right? And if you go back and think, it said, when we learned that fundamental theorem, it said, let it be any antiderivative. Why am I not putting plus c right here when I find that antiderivative? Why am I not putting plus c right here? Think about that for a second. What would happen, or what's going to happen, if I put that plus c right here? C is just a constant, right? I'm not going to plug in 10 into the c, and I'm not going to plug in 1 to the c. It's just going to be a constant. So when I do the evaluation, when I find the change, and when I find that difference, the c's will just disappear. So when we compute a definite integral, you don't even worry about the plus c. The plus c is only important if you're just straight up finding an antiderivative, okay? Without computing a definite integral. All right, so let's get back to this. The natural log of t. I'm going to go ahead and write this now like that because it's going to be easier for me to evaluate. I have you write it like this on your quizzes, so I know that you didn't use an online calculator, even though some of you I know did use an online calculator because you ignored the directions and you wrote it like that. But that's going to come back and bite you later. So here we go. We're going to now evaluate this. This is the natural log of 10 minus 1 over 10. And then I like to put that in parentheses, and then I put minus the natural log of 1 minus 1 over 1. I put that in parentheses. And now I'm going to just go ahead and leave this as the natural log of 10 minus 1/10. The natural log of 1 is 0. Minus a minus 1 is plus 1. So this ends up being the natural log of 10 plus 9/10. Okay? So if I wanted an exact answer for this integral, it would be natural log of 10 plus 9/10. If you stick this on a calculator or a Desmos, it's going to give you the decimal version of natural log of 10 plus 9/10. Okay? So that's both parts of the fundamental theorem of calculus. The part that says, hey, the derivative of a function that's defined as an integral is just take that x and put it down in. It's just the function inside the integral. And then the second form is, how do I compute a definite integral? I just find the antiderivative, and then I evaluate it at the endpoints and find the difference. Okay? So that's that. I'm going to give you problems in your book. I don't know if you guys remember that we had a book. But these are some problems in your book that I want you to work on. From section 5.3, 149 to 157 odd, and then 170 to 189. Okay, so work on those problems, and then when you're done, you're not going to start on these right now. Actually, you're going to stop this video. You're going to come back, and we're going to talk about and answer questions about anything that you might have. So, peace.